And so one thing that's nice about this result is it's an excellent example of what Gödel had in mind when he contemplated the possibility that large cardinal axioms might have predictions which were subsequently verified. In this case, the subsequent verification takes place in CFC. Then he went on to prove with John Steele that if you have much larger large cardinals, wooden cardinals, then all projective sets are determinate. And he's made other fundamental contributions to the theory of forcing, intermodal theory, and more recently, actually starting in 1976, he's turned to the philosophy of mathematics, and more recently he's done a lot of work in that area, in particular on conceptual realism and evidence in mathematics, and that's what he's going to talk to us about today.
Topic of the workshop, Frontiers of Incompleteness, through a discussion of what basic mathematical structural concepts, what they are, and what their role is in mathematics, and in what sense they might be complete or incomplete. I'm not here talking about the completeness of first-order theory, and what evidence we might have for the completeness and incompleteness. So I share probably with a number of people, but in particular on the opposite end of the spectrum with Gödel and Saul Pfefferman, the view that mathematics is about concepts rather than objects. Pfefferman talked here about his view during the workshop, so I'll say a little about Gödel's view. Gödel, in his the published version of his unpublished Gibbs lecture, said at one point, therefore a mathematical proposition, though it does not say anything about space-time reality, still may have a very sound objective content, as it says something about the relations of concepts. I don't know whether either Pfefferman or I would state it quite that way, but in both cases we think that mathematics is somehow about concepts and their relations. So some differences to some set my view with respect to Pfefferman's and Gödel's. Some differences. One is about what mathematical concepts are. Pfefferman takes them to be human creations. Gödel takes them to be objects. For Gödel, concepts are literally one of the kinds of objects, and they're objects in a non-spatio-temporal realm. Gödel differs from me, and I guess from Pfefferman, in thinking that our knowledge of concepts comes from a kind of perception, which he just calls mathematical intuition. And more sort of directly relevant to the theme of this workshop, Gödel is sure that the continuum hypothesis has a truth value. Pfefferman is sure that it does not have a truth value, and my own view is that we don't know whether it has a truth value. We really don't know. And I would like, I think it's an open question, may be settled any time or close to settled, but in some sense settled. I think it's still possible it's true, it's false, or it doesn't have a truth value. And I want to understand both answers to the question, does it have a truth value? An answer to how can it be possible that it has one, and also how can it if it doesn't have one truth value, how I want to understand how that can be, what it would be like. So the mathematical concepts I'm going to talk about are concepts of mathematical structures. By a structure, I'm going to not mean sort of, at least in one sense, a structuralist structure. I mean a bunch of objects and some relations and operations. I don't care whether the objects form another object a set, or whether the functions and relations don't necessarily have to be themselves further objects, as far as I'm concerned. The concepts I want to talk about are the ones, the subjects of what Pfefferman has called our fundamental mathematical axioms. At some point in a paper, a talk in a paper, he distinguished between axioms like the axioms for a group, which he called structural axioms, and the axioms of set theory, or the piano axioms for number theory, taken at least as fundamental axioms, which are not, the structural axioms are essentially definitions, and fundamental axioms are not, on the face of them, definitions. These basic concepts, we normally construe them as concepts of individual structures, each one a concept of a single structure, like the natural numbers, sets, the sets, and so on, rather than as a kind of structure. I actually don't think that's right in any of the cases, but I won't argue that today. Each of these, one thing about our fundamental concepts, we can study them, and often do study them, without a background or knowledge assumptions, without any background or knowledge or assumptions about other concepts. That is, you can study, as Dedekind studied the natural numbers using set theory. You could just study the natural numbers as forgetting that there are any such thing as sets, or not caring whether there are any such things as sets. Study them as a fundamental. The concept of natural numbers is a fundamental concept. So the concepts I'll talk about are the concepts of the natural numbers, and sets of natural numbers, and natural numbers and sets, et cetera, like that. And the general iterative concept of set and extensions, I would mind like extensions involving large cardinals. This is sort of a preview. Some aspects of my view are, one, that basic mathematical concepts are not so intrinsically different from ordinary concepts. I don't know what ordinary concepts are. I mean, I don't have it doesn't seem to be right, totally right, as Pfefferman says, that we created the concept of the natural numbers. It seems there's a sense in which we discovered the concept of natural numbers, but I don't want to go the direction Gödel does and put the concept of natural numbers into the basic furniture of the universe and put it off somewhere in another world, or put it in this world either, I guess. I think the main difference between garden variety, other kinds of concepts and mathematical concepts, is that they're sharp enough to support mathematical study. Basic mathematical concepts, insofar as they're basic, rather than being defined from other mathematical concepts. So the concept of the natural number, as opposed to is fundamental, as opposed to the concept of the natural numbers as something defined in set theory, defined as a kind of set. They don't come with anything like certifiably precise characterizations. We can explain them to one another, and I think make others understand them, but this is not because we have, it's not all there in at least some obvious, simple way in the words we use to describe them. We can communicate the concepts, but in some sense, Gödel insisted that basic mathematical concepts, or concepts like those of set and numbers and so on, the real concepts of which mathematics was about the relations of, could not be defined. And in the sense he was talking about, I think he was right. They cannot be defined. I think the natural numbers is, let me just to introduce a notion, is first order complete, that it determines the truth values for all sentences of first order, say, usual language of arithmetic. In language of Gödel, the concept implies each first order sentence or implies its negation. I think that the concept of natural numbers is, so that's what I mean. This is not a notion of completeness in the sense of a first order theory being complete. I'm talking about the concept of natural number. What facts about the natural numbers follow from the concept? I think all first order formulas are either implied or their negation implied, and I'll talk about why later. I think it's an open question whether the concept of set is, in a similar sense, first order complete. Particular, I already said, I don't think that we know whether the continuum hypothesis or its negation is implied by the concept of set. The concepts of sets and natural numbers are both, I think, categorical, and that we can prove them categorical, and they have, in fact, been proved categorical long ago, essentially. And by categorical, I mean simply that we know that neither of the concepts has non-isomorphic instantiations. By an instantiation of a concept, I mean a structure that of which the concept is true, of a structure that an instance the concepts are concepts of structures, and it's a structure that fulfills the concept. So I think they're both categorical, but I think it's open question whether the concept of set determines the truth value of every first order sentence in the language of set theory. So I'm not going to say much or argue about this, but I'm sort of agreeing with Pfefferman and Gödel, or especially Pfefferman, and I think also essentially Gödel, that mathematics is about relations of concepts rather than directly about objects. There are a bunch of reasons I guess why I think this, but one is I find the old Benacerraf problem about the connection between mathematical truth and mathematical knowledge a genuine problem. I think it's a serious question, and a lot of attempts to solve it seem to me to proceed by coming up with really strange kind of notions of mathematical objects, that they're thin, that you can, if you just specify their identity conditions, there has to be, that's enough somehow for existence. I mean, I have sort of an old-fashioned naive view of what objects are, and I think the Benacerraf problem is a problem. The other problem, which I'll explain later, is, or I'll give you a preview now, is what I'll call the categoricity problem. That is, there's certain knowledge that I think we lack, and they fail to explain how we can lack this knowledge, in a sense. So here's a quick explanation. I'll say more later. The concept, I'm going to argue the concept of sets of natural numbers is categorical. If it's instantiated, then it has in some, there's a structure that instantiates it that has some truth value. All structures that instantiate it have the same truth value. That seems to mean that it has a truth value. Now, there's some room to maneuver there, but I think maneuvering isn't plausible. So I think if it's instantiated and it's categorical, has truth value, And so if we knew it was instantiated, I'm not saying it isn't instantiated. If we knew it's instantiated, we'd know this continuum hypothesis has a truth value, and I take it an empirical fact that we don't know the continuum hypothesis, even whether it has a truth value. So there's a property I think short of being instantiated, but if you want to say it implies being instantiated, as I won't quarrel, a property of concepts that has all the important consequences of instantiation. Now this is, I think, a questionable concept. I'm not sure that I can describe it adequately, and you may not be sure there's anything I'm failing to describe adequately. But let's say that a concept is fully determinate. If it determines in full detail, it determines exactly what a structure instantiating it would be like. One way one might think of this is it determines a structure, but a specific structure in all its detail. I think most of us probably think the concept of the natural numbers as having this property. I do. Full determinateness follows, I think, from categoricity plus instantiation, but full determinateness seems to me what we want our basic concepts to have. I don't think it's so important whether or not there are actually some objects that instantiate them. It seems it does all the important work of instantiation, and I don't see why it implies instantiation. However, since all my misgivings about basic concepts being instantiated are basically misgivings about their being fully determinate, I'm not unhappy if someone wants to claim that a fully determinate, that since the natural numbers are fully determinate what they're like, that there are natural numbers. Fine, go ahead. I don't mind. That's all right with me. I was going to. I decided the talk would be too long to do this. I wanted to talk a little, say something about Gödel on the role of objects in mathematics as opposed to mathematical, what we would call mathematical objects as opposed to mathematical concepts. So I'll just say a little briefly. Charles, in his talk, discussed, I think, very, very well Gödel's views, not just on objects, but his general views. So let's say, so Gödel sort of different from Frege, classified objects. The general classification is objects. This is different from Frege. And there are two kinds of objects. There are concepts and things. And he was very important that concepts are objects. They're really part of the real, what the difference with Frege on this point is, I'm not at some deep level sure, but they are objects. He contrasted his view with Aristotelian, which he called Platonism or conceptual realism, with Aristotle's view that concepts aren't actually objects. Gödel says so this, what does he say about mathematical objects? One, he thinks that there's just as much room to believe, he says, in mathematical concepts and objects' existence as there is in whatever, I forget, anything, the existence of physical objects. He also, when he talks about our having perception of mathematical objects, he talks both about perception of things like sets and the like, but also perception of concepts. But he talks about both of them. His epistemology seems to be based on our perception of mathematical concepts. If you look at, there's nothing that I see that he says anywhere that explains how we would get could get any knowledge from his kind of perception of sets or numbers
rather than the concepts of these kind. I don't really see what the difference is supposed to be between his perception of concepts and ardent variety understanding or grasping concepts in some other sense, but he does. One place where he seems to make a use of mathematical objects is when he argues in both versions of his continuum hypothesis paper, but in a little different way, that that if the concept of set is, and now I forget, Charles, what's the word? If the concept of set is something, there has to be a realm of objects where it is.
Where he talks about describing a well-determined reality.
Yeah, well-determined reality. Yeah. If it's, was it coherent or consistent? I just forget the word. But if some positive word, then there must be there's a realm of objects of a realm, a world or something in which it's true. Of course, there could be a world, there could be more than one world, you might think, and in some worlds they might, the continuum hypothesis might be true. He doesn't really argue that that the realm of objects has to be the same, so he seems to be implying for the concept to have this desirable property which implies instantiation for him, it should seemingly be at least determinate enough to determine the truth value of the continuum hypothesis. But in any event, he does think mathematical concepts are instantiated, and he seems to think the concept of set or something is categorical from this argument, or it's categorical if it has this other good property he thinks it has. I don't see why you couldn't have a perfectly fine mathematical concept. That's why why it has to be instantiated, or what one gains from it. Anyway, I don't want to say any more about that now. So I want to first talk about the concept of natural numbers, and I won't distinguish between the concept of natural numbers and the more simply the concept of the ordinary infinite sequence or an omega sequence of objects. The concept of an omega sequence, or that of the natural number sequence, of course, may not be taken as basic, but as defined, usually defined from the concept of set. But throughout this first part of the talk, at least, I'll take the concept as basic. An instantiation of the concept will consist of some objects and a function, the successor function. If one wishes, one can think of this successor function as a relation and not an additional object. I don't draw, although it's very important in first order theories, I don't draw a big distinction between the concept of an omega sequence with just the successor and the concept of the omega sequence with addition, multiplication, or exponentiation, or what have you. They're all recursively definable. So it seems to me the facts about those concepts also follow from the concept of the number sequence just as a set with a successor function. This is about the undefinability of the concept. There are various ways we can describe the concept of the sequence of omega sequence, or of an omega sequence, or the sequence of natural numbers. We can say it's like a sequence of telephone poles or something, or going on forever, or there are various versions, or it's 1, 2, 3, and so on, and then if you're more sophisticated, and there's nothing after that, or it's an infinite sequence where every element has an immediate successor, but each element has only finitely many predecessors. So one can either sort of talk metaphorically or something, or one can use words like finite, but there's a circle of words, and somehow we somehow, to get the concept, have to understand some word in that circle. And we don't have any, except in terms of some other concept like set, defining the concept directly. In asking whether the concept is first order complete, let me just think of it as complete for the usual piano axioms, or piano language of piano arithmetic with s plus and times. I suspect that most mathematicians believe that the concept of an omega sequence is first order complete, but I also suspect, as they think as I do, that it's fully determinate. One might describe this permanent determinant, as I said a while ago, as saying that fully determines a single structure, but I don't want to take determinate as to imply there is something which is the structure that it determines. So this is just as I said before, it's fine if you think it being fully determinate implies that the natural numbers exist or an omega sequence exists. I don't tend to follow you, but it doesn't matter that much. So next I want to talk about axiomatization of the concept. So what I call the informal piano axioms are the usual piano axioms, except by the informal as opposed to first or second order. I wanted to take the induction axiom in a particular way. So what are the axioms usual? 0 or 1, whatever one start with, is not a value of the successor function. The successor function is 1 to 1. For any property, if 0 has the property, and if s of x has the property whenever x has it, then everything has the property. So this is the induction axiom. I stated it with any. Bertrand Russell had some distinction between any and all was an actual quantification, and any was supposed to be created schematically. He was trying to get around the problem that by his own theory he couldn't actually say all about much of anything, so he couldn't state his own theory. But I would like to think of this P as a sort of equivalent to an open-ended schema, but if you don't like schema in the sense that if one is, now I've switched from 0 to 1. That's not supposed to be an important difference. If 0 has a property, has property P, and s of x has P whenever x has P, then everything has P where you can put anything in for P, whatever language, no restriction. The main thing is it's open-ended. I'm not claiming real second order, if you think of the second order piano axioms, I think of something where it's supposed to be fully determine what you're talking. It's supposed to be, it should admit nested quantifiers. Whereas I think, I'm not assuming the existence of anything when we're talking about the axioms, they're the objects it's talking about, the natural numbers or the elements of an omega sequence, but I don't want to have it to make use of any other objects. And second order logic thinks it's at least sensible to talk about second order quantifiers, to nest them and so on as if they have determinate determinate meaning, where I don't think that's at all clear that they do. So so I think of this, you can use the axiom if you're sure you've got a definite property, then you can use the axiom, but we don't sort of have in general any feeling what the negation of the axiom would say. So the informal piano axiom should not be, I think, confused with the second order piano axiom. I think Pfefferman in his talk here, or at least the paper for the talk, seemed to say something similar about either this quantifier or the set theory one, I forget which, but I think he and I, at least on one of these cases of a universal quantifier over property-like objects are in agreement. So I think it's plausible to say that the piano axioms fully axiomatize the concept of an omega sequence. I think it's hard if you try to think about trying to argue that from the concept. It's not so clear, but I think it's very plausible. So they fully axiomatize the concept, so that whatever follows from the concept follows from the axioms. I think that this is plausible. So a concept, as I said before, is categorical if any two structures instantiating it are isomorphic. the piano axioms are categorical, so I'll argue that in a second, but I'm just giving Dedekind's argument. Claim, since the piano axioms are categorical, and they're implied by, maybe are equivalent with, the concept of an omega sequence, the concept of an omega sequence is categorical. So I'm just going to present a version of Dedekind's, or any various proofs that the natural numbers are, the concept of the natural numbers or what have you is categorical, but I want to be careful. Dedekind presents his proof basically in set theory, and I don't want to particularly be assuming that there's any principles from set theory or that there are some further objects. So I mean, here's the object. Suppose M and N are omega sequences. So both M and N satisfy the informal piano axioms, or we're arguing that the piano axioms are categorical. You suppose M and N satisfy the piano axioms. So we specify basically by recursion that a function sending objects from M to objects in N, namely, that f of 0 is the 1, 0 is the 0 from the other structure, and f of the successor of an object is the successor of f of an object. And using the informal induction schema, you can show that this, is an isomorphism. Of course, it's not explicitly definable, but it's defined in I think an important way. So we don't especially need to think of this f as an additional object somewhere. We don't have to worry about the general notion of a function or anything like that. This is explicit. Function is given, or not explicit, it's recursively defined, but it's given in terms, there's nothing ambiguous about it or dubious about it. Or about the properties that we would use in proving that it's an isomorphism. So if we'd considered symbols for addition and multiplication, we could have, given the usual arguments that by induction that this map is an isomorphism with respect to them. So the categoricity of the informal piano axioms doesn't by itself imply the first order completeness of the axioms or the omega sequence concepts, for the trivial reason that categoricity implies nothing if there's no structure satisfying the axiom. Dedekind himself was, of course, well aware of this and attempted to give a proof that an omega sequence existed and which people have mostly made fun of. But I think he was serious to want to try to show it. What I suggest is that the real reason for our confidence in the first order completeness of the natural numbers is not our categorically, but is the full determinateness of the concept, which we don't get through an argument, but through sort of way we understand the concept. So I think it's the only legitimate justification we have of the assertion that the concept is instantiated or that the natural numbers exist. So let me switch now to the concept of set. So the modern concept of set you might think of as having four components. One doesn't have to break up into the separate ones. One's the concept of natural numbers. Second, the concept of what Gödel calls sets of x's. Third, the concept of transfinite iteration. And fourth, the concept of absolute infinity. We probably should include a 0 for the concept of extensionality or something, but I'm not doing it. And of course, we don't have to talk about the natural numbers separately, but I've already treated them as separate. Again, it's a concept that I take even not just number theory, but set theory to be a concept of a kind of structure, not of some individual structure, but I'm not arguing that here. So roughly speaking, how do all these four concepts come together? A set structure is what's gotten by starting with, say, the natural numbers and transfinitely iterating the concept of sets of x's, which I'll talk about in a minute, and absolutely infinitely many times. So a set structure, you might, of course, we could also just start with the empty set and iterate the concept of set of x's and absolutely infinitely many times. The phrase, as I've said, comes from Gödel. The idea of sets of x's, the x's are some objects. The sets of x's are the sets whose members are x's. Gödel says about this concept in where I think gets the continuum hypothesis paper, that the operation set of x's cannot be defined satisfactorily, at least in the present state of knowledge. I'm not sure how he expected the state of knowledge to improve so we could define it satisfactorily. It doesn't seem to me it's like his other concepts that that it's the other basic mathematical concepts that he claims are not definable. It cannot be defined satisfactorily, at least in our present state of knowledge, but only be paraphrased by other expressions involving, again, the concept of sets, such as multitude of x's, combination of any number of x's, part of the totality of x's. But as opposed to the concept of set in general, if considered as a primitive, the concept of set in general, we have a clear notion of the operation. So Gödel, in his Gibbs lecture, one of the things, one of the first things he said was that it was impossible to axiomatize the concept of set, but this was because of the absolute infinity. It wasn't. So I think he does seem to talk about the concept of set of x's actually being axiomatized. So he thought in some sense it was axiomatizable, but in the concept of set, the whole transfinite hierarchy, not so. So he thought there's a difference here, but I don't know why he's talking of as if it might actually be defined in some sense or other. So for Gödel and for me, the concept, I think Gödel basically holds the same, is like the concept of natural numbers, typical of the basic concepts of mathematics. It's not definable in any straightforward sense, or at least in the present state of knowledge. We can understand it, communicate it to one another, though what we literally say in communicating it by no means singles out the concept in any clear and precise way. I take it that our ability to understand this and other such concepts is striking an important fact about us. Gödel says that the concept of set of x's is clear. Fefferman says that the concept is unclear for the case when x's are the natural numbers, so one would presume for the case when there are infinitely many, any case when there are infinitely many x's. Fefferman says that the concept, at some place at least, says that the concept of arbitrary set of natural numbers is vague. My own view is that the clarity or unclarity of the concept of sets of x's is an open question, and that we cannot rule out that the answer varies with what the x's are, even if restricted to the case there are infinitely many x's. So the general concept of set of x's is a concept of structures with two sorts of objects, and now I just want to look a minute at the general concept, and a relation we call membership that can hold between objects of the first sort, the x's, and objects of the second sort, the sets of x's. Clearly the following axioms are implied by this concept. If sets alpha and beta have the same members, then alpha equal beta. So that's sort of part of the general extensionality of the notion, kind of the notion of sets. And two, for any property P, there is a set whose members are those x's that have P. So these are sort of the informal axioms Axiom 1 is extensionality. Axiom 2 is a comprehension axiom. I take it as an open-ended schema, like the induction axiom, which I call the informal comprehension schema. Do these axioms fully axiomatize the concept of set of x's? I think it's plausible to say they do, although I'm not, once again, don't see a clear proof that they, I would argue that they do. Gödel seems to have thought so, or maybe thought so, I don't know, maybe too strong. In the published version of the Gibbs lecture, his Gibbs lecture, he says of the case, this is of the case when the x's are the integers. For example, the basic axiom, or rather axiom schema for the concept of set of integers says that given a well-defined property of integers, that is, a propositional expression phi of n with an integer value n, variable n, there exists a set M of those integers that have the property phi. It is true that these, so I think I've omitted some discussion of why the axioms aren't, he's trying to argue the axioms are true in virtue of meaning, but he doesn't want them to be called tautologies, and I think I've missed something in the middle. He says it's true that these axioms about tautologies are valid owing to the meaning of the term set, and one might even say that they express the very meaning of the term set, and therefore they might fittingly be called analytic. However, the term tautological, that is devoid of concept, is entirely out of place. So I take it that Gödel is talking about, when he talks about these axioms, something pretty close or the same as what I have in mind in talking about the informal comprehension axiom. He's talking only of the comprehension axiom. There's a similar section in Gödel's earlier paper, Russell's Mathematical Logic. In it, there's a passage similar to the one I just quoted, except that Gödel there adds the axiom of choice, saying that nothing can better express the meaning of the term class than the axiom of classes, which is the corresponding comprehension axiom in Russell's theory, and the axiom of choice. So does one need the axiom of choice to fully axiomatize the concept of set of x's? You might think we either needed to have it or something the other direction. I suppose that depends on how one construes the term property involved in my version of the informal comprehension schema. So I'll say a brief thing about this in a few minutes. Gödel does not mention extensionality, but clearly it is necessary for a full axiom to fully express the concept of sets of x's. Axioms 1 and 2, I claim, are categorical for a set of x's in the sense that there cannot be two instantiations of the concept with the same x's. Here's the proof, essentially due to Zermelo, whose separation axiom should, I think, like the informal, be viewed as an open-ended schema. So here's the idea, this is basically Zermelo's proof. If M1 and M2 are structures satisfying comprehension and extensionality and have the same x's, so we're both sets of x's, they have the same x's, then they have the two membership relations. So what's the idea? I mean, if one of them has a set has something that's missing from, if they're not isomorphic, if there's a set in one sense that's not a set in the other sense, then we can use the informal comprehension schema applied to the x's that belong to the set in the one sense to contradict the informal comprehension schema for the other set. So one can construct an isomorphism like this, namely for each set on the one thing, you look at the set with a set in the other sense that has the same members, there always has to be one by informal comprehension. So some comments about this argument, that the properties using in the argument are defined from the given structures. That is, there wasn't any, granted that these structures are legitimate structures and instantiate, satisfy the axioms, then we've got the properties we needed for the proof. The isomorphism was defined. You don't have to think of it as an added entity. You can modify it if instead of the same x's, there are x's and y's, but we're given a 1-1 correspondence between the x's of one structure and the y's of the other structure. In particular, the x's and y's could be the objects of isomorphic structures, say instantiating some concept, for example, the concept of an omega sequence or the concept of the set of z's for some z's. So two key cases of sets of x's are the natural numbers and the natural numbers and the sets of natural numbers. So I won't worry about, just shifting to set theoretic terminology, I won't worry about the concepts of sets of these x's, the difference between that and the concept of subsets of v omega and the concept of subsets of v omega plus 1. So are these concepts fully determinate? Are they first order complete? The continuum hypothesis is a first order statement about the subsets of v omega plus 1. If the concept of v omega plus 1 is first order complete, the continuum hypothesis has a definite truth value. I take it, as I've said, to be a fact about our present state of knowledge. We don't know it has a truth value. So we don't know at present whether the concept of subsets of v omega plus 1 is first order complete. A fortiori, we don't know that it is fully determinate. This, I contend, implies that we do not know that there's any structure that instantiates the concept of the subsets of v omega plus 1, because if we knew there was such an instantiation, by categoricity, we'd know that there's a unique truth value of the continuum hypothesis, that it has in some, and so all instantiations of the concept, we'd at least have a very strong evidence that the continuum hypothesis is true or false or what have you, that it has a truth value. The case of the concept of v omega, or equivalently the concept of the natural numbers and sets of natural numbers, is very different. The standard first order axioms for the concept are what are called second order arithmetic, as has been discussed in Peter, in the articles Peter wrote for this workshop, for example. By adding to these axioms the schema of projective determinacy, one gets a theory that seems to be as complete for the concept of subsets of v omega as the piano axioms are for the concept of the natural numbers, and for whose truth there's a large and diverse, and to many of us, convincing body of evidence. So is the concept of v omega, could it be fully determinate? Do we have evidence of this? So one kind of evidence we would have, the kind of direct intuitive evidence we seem to have for the natural number concept being fully determinate. One would think that if we had that evidence for the sets of natural numbers, that the concept of sets of natural numbers was determinate, it would sort of be a special case of a general direct intuitive evidence that the concept of set of x's was fully determinate. At least the concept of set of of x's, where x's are objects instantiating some, where the x's correspond to some fully determinate concept. So if there were such evidence, it's hard to see why it wouldn't show that the concept of set of x's is fully determinate in general, and then if one applied this to sets of natural numbers and then applied it to sets of natural numbers, we would get that the concept of subsets of v omega plus 1 is fully determinate, and I think we at least don't know that, so I'm doubtful about the intuition. I do believe that I believe that 1 and 2 do, this evidence we have, provide evidence, this is incoherent, what they do imply evidence that all first order statements about V omega have truth values. I also believe that they provide evidence that the concept of V omega is first order complete, but I regard them as less strong evidence for this. So this may look like I'm contradicting myself. I think they're evidence for the truth. They're also evidence for the first order categoricity of the concept, but I treat these as different. I'll explain why in just a minute, because I better finish. Let's see, I'm going to skip, I have talked about the other components of the concept of set. I'm going to skip that part of the slides. I don't, good.
You can have more than 50 minutes if you want. We've got till half
Oh, I don't have more than about 5 or so more minutes anyway, and I was having doubts as to whether to talk about. So I don't see any special reason to, I don't see a convincing argument, but I don't see any special reason to worry about whether or not worry about whether or not the concept of, I see no block or possible block like the continuum hypothesis problem for the concept of a well ordering, or the concept of ordinal numbers, or a concept of initial segment of L. There's a problem about the length of absolute infinity, but forgetting that, I don't see any. I don't see why. Maybe there's some way to see the concept of initial segment of L is fully determinate. I'm not claiming that, but I don't see any special problems with it. Doesn't seem, it's different from the natural number case, but I'm not sure that it's that it's as different as the concept of set of sets of natural numbers seems to be. So I've been giving an account of basic mathematical concepts that might make you think that the way I think one's supposed to do mathematics is you investigate what's implied by the concepts. If you want to study the natural numbers, you should prove things about the natural numbers. You should, get principles you can get directly from the concept of natural numbers, and that would include the first order piano axiom. So it would include some more things, but anyway, we should go directly from the concept. It would seem to demand, in the case of the natural numbers, using only the informal piano axioms in some way. In the ZFC, in the set case, using, in the case of sets of natural numbers, using the informal piano axioms, extensionality and comprehension, and perhaps choice. Oh, I didn't remark about choice, it was on the slides, but I didn't say it. The argument for categoricity doesn't use anything about choice. So I guess one way to think about that is the categoricity is going to hold at least as long as you don't choice. There's no restrictive notion of choice, whatever that means. But, anyway, so you think this is, I'm claiming you should be just deducing things from the concept. But this is not at all the only thing that happens in practice. In the arithmetical case, many assertions that can be stated in the language of first order, say piano arithmetic, have been proved in second or higher order number theory, or first order ZFC, or from large cardinal axioms or something. Then they're not provable, known not to be provable in first order piano arithmetic. So a sort of standard case of this, needs to assume the consistency of things. It's consistency of various kinds of consistency of ZFC, consistency of large fragments of ZFC, etc. Strong consistency statements are equivalent to number theoretic statements. They're not, we can't have no clue as to how to prove them from the sort of directly from the concept of the natural numbers. This phenomenon occurs at every level. Statements about sets of natural numbers are provable in ZFC, but not always, but not in second or higher order number theory. There's almost always no clue as to whether or not they, whether or how they could be deduced in second order arithmetic. And often we have proofs that they can't be proved in second order arithmetic. Modulo worries about the inconsistency of something or other. The problem also seems to occur with respect to the full concept of set. I mean, for example, Wooden, when he's working in his program to prove, to settle the continuum hypothesis, I guess it's to prove it at present, always assumes the existence of a proper class of Wooden cardinals. One might wonder whether this can be justified only by a concept, not whether or not it's justified in doing it in some way, but whether it can be justified just on the basis of the concept of set, the iterative concept of set, or is he working with a stronger concept? By the way, there's no reason to think, it would be a real pipe dream to think that in these cases, when statements about a concept are proved from a stronger concept, that a direct proof from the weaker concept will be found. People used to say, oh, you should have the second order axioms of set theory because they're much more powerful and could imply much more things, but they're pretty useless. So I don't think there's any reason to hope that we can miraculously find a way to directly use the concept of natural number to prove the consistency of, say, second order number theory. Those of us who believe that the concept of natural numbers is fully determinate thus have to live with a very high probability that, for example, either ZFC plus there's a measurable cardinal is inconsistent, or else there are truths of number theory that can be known only by knowing that ZFC plus a measurable cardinal is consistent, or some such state. So evidence for the latter alternative is, I would think, evidence for ZFC plus there is a measurable cardinal. So can we be justified, should be a question mark here, in thinking that theorems about one concept proved using a stronger concept are implied by the weaker concept? Yeah, in the case where the weaker concept is the natural numbers, or another concept we know to be complete, sufficiently complete. So for example, let's say there's good evidence the concept of sets is consistent. The concept of set implies in a natural way that the concept of the natural numbers. The concept of natural numbers is sort of contained in the concept of set, right? We can get a structure that instantiates it from the sets given by the concept of set. The concept of the natural numbers is fully determinate. So for any statement of phi about the natural numbers, structural statement, first order statement in particular, the concept of the natural numbers implies the truth or falsity of phi. So I'm now assuming the concept of natural numbers is fully determinate. Thus the concept of set implies whatever the concept of the natural numbers implies, and if it's consistent, it cannot also imply the opposite. So I think it's okay to use the concept of, if you're convinced that the concept of natural number is fully determinate, there's some justification using stronger concepts that you only have reason to think are consistent or something in proving things about the natural number. So does it imply, does this kind of argument apply at a higher level? Well, it depends on whether or not we have evidence for full determinateness at some higher level. And I don't think we have direct evidence. I said earlier that we did have strong evidence for that yield a first order theory of the subsets of V omega. this fact counts as evidence, whether or not convincing, for the first order completeness of the subsets of V omega. It's for many of us convincing that the axioms, determinacy axioms, are true. Is it evidence that these axioms are implied by the concept of subsets of V omega? And the problem about this is hesitating about saying evidence is the evidence is that one's getting here is all intrinsic. So one kind of intrinsic evidence is this just evidence about one concept gotten by using a stronger, given by proof from using a stronger concept. It gives intrinsic evidence about the stronger concept, but only extrinsic about the other. So there are various attitudes one might have about this. One might think it's just in this, that our basic concepts are not fully determinate, but might hope that, so to speak, that all of our concepts together are enough to determine truth values for questions about any of our concept, but that we have to go to higher and higher levels. And so that's one attitude, that our concepts and our extensions of concepts are not first order complete, but sort of taken together, they're complete. Another possible thing is to take proofs of something about, say, the natural numbers from a higher level thing, or the sets of natural numbers from higher, stronger concepts, as evidence that the thing proved true holds of the lower level concept. And I want to suggest, I don't know whether this is either something suggested to me by Peter Koellner or something suggested to me by misunderstanding Peter Koellner. So one way, it seems you might justify thinking that proofs from a stronger concept of things about a weaker concept to justify this is that we make a methodological defeasible assumption that our basic concepts are fully determined, or perhaps even that they're instantiated. And then when we prove something, a phi from a weaker theory using a stronger theory, this shows relative to as long as we have reason to think the stronger theory is consistent, it shows its evidence relative to our general methodological assumption that the thing we proved about the weaker system is true and in fact implied by the weaker concept. So this does still leave us to the problem of explaining the validity of other kinds of extrinsic evidence, like the evidence for determinacy, say. One thing I would like to point out about that is a lot of that evidence seems to me just forget about what your theory is about, what mathematics is about. It just seems like to me evidence for truth, not evidence for methodologically being right or something. So this is the sense in which I think if you forget the metaphysics or whatever, just think of epistemology. It feels, a lot of this evidence just plain feels like evidence for truth, whether truth about one concept or proof about the other concept. So I think this methodology suggested fits nicely with regarding such evidence as evidence for truth. And it's at least makes clear what, relative to the methodological assumptions, what we're trying to do when what we can think of ourselves as doing in proving these things from stronger statements. So I want to conclude with quoting Pfefferman in his paper from his talk here, quoted something from Gödel, but also quoted, catch me saying things, that evidence against myself. Throughout a statement I made in 1976, throughout the latter part of my discussion, Pfefferman says, excuse me, so I say, this is me. in 1976. I've been assuming a naive and uncritical attitude toward the continuum hypothesis. While this is in fact my attitude, I by no means wish to dismiss the opposite viewpoint. Those who argue that the concept of SAD is not sufficiently clear to fix the truth value of the continuum hypothesis have a position which is at present difficult to assail. As long as no new axiom is found which settles CH, their case will continue to grow stronger, and our assertion that the meaning of CH is clear will sound more empty. I rarely understand my earlier self. Seems usually to be confused or unintelligible. But in this case, I think it's natural to interpret the first part of what this young fellow says, by this is in fact my viewpoint, as a declaration that he is following the methodology I've been discussing and assuming that, all our concepts are fully determinate and just kind of working relative to that assumption. I don't disagree with what this young fellow says in the last sentence, either with one qualification. I do think that time going by without the continuum hypothesis being settled is evidence on the other side. But the qualification is that one, what I and others regard as a success in finding very probably true new axioms that answer questions about subsets of V omega and about L of R gives some reason to be optimistic about finding possibly true axioms that settle a continuum hypothesis. And moreover, I think particular Hugh wouldn't, but other, I think there's more sort of direct reason to think that new axioms that do settle the continuum hypothesis or new principles may be found than there certainly was at the time of May 1976. Anyway, sorry to run us so far over. Thank you.
Hello. So I was a bit unclear what the difference between fully determinate and categorical was.
So categorical means that any two structures that instantiate the concept are isomorphic, and one difference is that can hold just any time there are no structures that instantiate the concept. Let's see, I don't see if you take categorical plus instantiated, I don't see, although there is room for an if you think of the concepts as being the basic thing and what's implied by the concept, then you could still think, oh, it so happens that all the structures that instantiate this concept are isomorphic, but it doesn't follow from the concept. So there is that room, but that doesn't seem to me very plausible. So I think I tend to not see a difference. But granted instantiation, I don't see a difference between being categorical and fully determinate. I think fully determinate is, yeah, it's just, but only with instantiating.
I think earlier in the talk you said a concept can be fully determinate without being instantiated, right?
Well, so I guess I said two things, and maybe I got at some point what I literally said wasn't consistent. My own feeling is I don't see what's wrong with a fully determinate, uninstantiated concept. Why does it have to be? Why did there have? I mean, I have nothing against abstract objects. But I don't see anything wrong with that. But since my main worries about people easily assume concepts are instantiated, like there's every consistent concept is instantiated by something, or every consistent theory, and so people say this, and the worry, the bad things I think about their saying it I would say about people who assume that concept is fully instantiated. In the cases like the concept of V omega plus 2, where we don't have, there's reason to doubt that the concept is fully determinate. I don't care so much about the difference. So I, for myself, don't see what's wrong with a fully determined, uninstantiated concept.
I could, finger on this point, like, so this is zooming in on your proposal to reconcile like the categoricity with the idea that still we don't know whether there's a right answer about CH. It seems like you say, yeah, I admit that, if the thing is instantiatable, any two instances are going to be isomorphic, and so they've got to give the same verdict about CH. But it might be that it's not instantiatable.
Yeah.
So it seems like, on your view, the sense in which it might be that there's no right answer to CH is the same sense in which in which it might be that there's no right answer to CH, is a sense in which, if that's true, then there's no right answer to, is the empty set identical to itself?
No, I don't think so.
Okay, so yeah, that's, so.
No, so look, I think one could talk, I'm talking about the admittedly not precise notion of what's implied by a concept. So I think that all the axioms of ZFC are implied by the concept of set, that the existence of inaccessible cardinals are implied by the concept of set, and so on. So I think we should certainly regard these as truths about the concept of set, but that doesn't mean that that the concept that there has to be some structure to me instantiating, or that there have to be answers to all the questions. I'm trying to think a possibility, a live possibility. I hope it isn't the truth, but a live possibility is that the concept of set, doesn't decide everything, that there are, that Pfefferman is right about the concept of set. And now I'm trying to understand how that can be, and the only way I can see is if there's no instantiation. But that doesn't mean that things don't follow from the concept of set, or that the axioms of set theory aren't true. I think at least anything that does follow from the concept is implied by the concept of set. In fact, anything provable from the ZFC axioms is true about sets, true about the concept, and so on. But there may be things that are neither true or false, and I think that can happen only if the concept is not instantiated.
So if it turns out to be incoherent, then some kind of formalism or something steps in.
I don't see that that's in. I think this maybe I think Charles and I have a different. Charles talked about coherence, which I think he took in a perhaps stronger way than I don't see what I think the concept of set is coherent. I don't think coherent means that it's a coherent concept, but it may not decide all the questions about itself. I don't.
Right, but you also think it's, in particular, you think it might be uninstantiatable. That's what was tempting me to think that.
Well, but I don't see why what's incoherent about being uninstantiated. As far as I'm concerned, maybe no concept is instantiated. I'm not committed. I don't think instantiation is important for pure mathematics. We're trying to see, if there are studying basic mathematical concepts, we want to find out what has to be true if these of anything instantiating the concepts. What does it matter whether or not there is anything? I mean, if mathematics applies in the standard ways to physics, then that's involving instantiations of concepts. Yep. Sorry. Go ahead.
Sorry, it looks like this is the last follow-up because other people haven't. I didn't mean to, but it looks like I can see that actual instantiation isn't important. It looked like you were suggesting this other way that mathematics could be the investigation of what's necessitated by our concepts. It could be the investigation of what is it that any structure that satisfies this concept has to be like.
Well, I think it was any structure in some logical sense that would satisfy the concepts. It can be a counterfactual.
Right.
It could be. Yeah.
Anything that could satisfy this.
Or would, yeah.
So, so now I'm trying to reconcile that picture with your acceptance of the categoricity of our informal axioms for set theory, and your idea that there might not be a right answer to CH. Because it's looking like the scenario in which there's neither, the epistemically possible scenario in which there's not a right answer to CH is one on which, oops, it turns out that no structure could instantiate our concepts of set.
Or that,
So
at
it
least
looks like you're
no,
sort of,
no structure does, but I would tend to say, so,
I mean, because if some structure could, then by categoricity, they would all agree on CH. So it
well, it
seems
depends
like
what you mean by the could, or, and so now we get into, I mean, I think there's, you can think of, what would have to be true of a structure that instantiates a concept is a kind of modal about possibility. I think I take it as a kind of logical possibility. I think, you know, it may be, so think in terms of this possible worlds of this kind. I mean, I don't think there are possible worlds in it, but it's possible the continuum hypothesis is false in this sense. It's not determined by the concept. It's possible the continuum hypothesis is true. Maybe both are possible. That's the uninstantiatable concept. Now, if you take some modal notion of set theory like Jeffrey Hellman, Hellman will argue, well, there's a world where the continuum hypothesis is true. There's a world where the continuum hypothesis is false. If we had categoricity, then he would argue that we could prove the structure in one world that makes it true is isomorphic to the other world that makes it false. So, but I think about, but he's assuming fully that one thing I want to think about these possible worlds is they're not fully determinate. They're not just because they're not, they don't have real objects in them. They're only sort of, they're like stories or uncompleted stories. So admittedly, you're right. I'm saying that if the continuum hypothesis doesn't have a truth value, then there really is no fully determined structure that satisfies the axiom of set. And if that you count that as incoherent, then yeah, then it's incoherent. So I still think it could be it's an important concept, even if it's incoherent in that sense.
I have a follow-up. So it's about determinateness and instantiation. So first of all, I agree with you that we don't know that CH is determinate. And I do think that first-order statements about arithmetic and even second-order statements about arithmetic are determinate. So the
You think we know this now?
Yeah, because of the case for axioms of determinacy.
Oh.
So I think the first-order arithmetic is determinate, second-order arithmetic is determinate because of the case for the axioms of definable determinacy.
Mm-hmm.
Yellow bar. But and the real crux of the matter is at the level of CH.
Mm-hmm.
But I want to ask this question about full determinateness. So it's a primitive notion, so you can't really explain it through more fundamental notions, but we can try to get structural understanding of it. So the structural understanding of it I have is, from your talk, that it's the epsilon such that categoricity plus epsilon implies first-order completeness. It's the thing you have to add to categoricity to get first-order completeness.
Let's see.
Categoricity itself doesn't imply first-order completeness because it could be vacuous, and we know that if you add instantiation.
So certainly, if you add it to first-order completeness, you'll get. If you add it to categoricity, you'll get first-order completeness and more. But I don't know that it's. I mean, that's not how I don't think of it in terms of related to first order at all. I think something like, we know, you just know exactly what it's like. I mean, it's determined in sort of, I admit, this is a problem notion that's hard to understand. I think we sort of know what the natural numbers have, know what they have to be like. There's no room for, there's no, it's just as if they were there. They were there. It's if they were.
So let me put it this way. So categoricity of, let's say, first-order arithmetic does not, on its own, imply that every statement of first-order arithmetic has a determinate truth value because of the vacuity problem.
Yeah.
And we know that if we have instantiation, then we've got a home run. And
Yes.
we've got that every statement is
Okay.
determinate. And you're trying to find something that falls short of instantiation, which when added to categoricity.
But yeah, I think,
gives it. And
that's,
this is it.
yeah.
Is that
This
the
is
right way to
it,
understand it?
but yeah, if one's trying to characterize it as, I don't know, yeah, I fully admit this does that, but I thought you were also saying that exactly what it consists in
Well, I'm just
is
trying
what's
to.
missing from,
I'm just trying to understand why you're going to that without going to full instantiation. And the way I try to get a grip on very metaphysical questions is by this sort of thought experiment. If suppose I died and went to heaven, and I was talking to God, and God said, first order arithmetic is categorical, and every statement about it has a determinate truth value.
not just
And
every first order
Every
statement?
first order statement about it has a truth value. And then I would think at that point that, okay, so there's infinitely many prime numbers, and the concept of natural numbers instantiated. But then if God went on to say, but no, it's the case that all the statements of first order arithmetic have a determinate truth value, and it's the case that it's categorical. But as a matter of fact, the concept of natural numbers is not instantiated. As a matter of fact, there's no natural numbers. I would think that that is bizarre.
Right. So, let's see, so what, so you would say it was bizarre, there are no natural numbers, there are, it's categorical, and
Every statement of number theory has a determinate truth value.
every first order statement has
Yeah.
determined truth value. Yeah, so, I mean, I find it bizarre about the natural numbers, but just because I think that
It's just that in your picture, that's a coherent thing to say, so it's possible.
well, it's coherent about a concept, yeah, that it was, that maybe there's some concept that sort of determines all the first order truths about it, but not all the truths, and isn't,
So it
well,
would be the case that the concept of natural
well,
numbers
an example, well, no, so I don't think, yes, I guess, go ahead.
So the situation is that the concept of natural numbers is determinate, it is categorical, and it's fully determinate. So every statement, first order statement about the natural numbers has a determinate truth value.
Well, it's just sort of every,
And yet
yes.
there's no natural numbers.
Well, I don't, it's hard to say about the natural numbers, but if you're just talking about might it be the case for, I don't particularly think it's plausible for some level of set theory, but let's replace that by the level of set theory. I don't see anything incoherent about the idea that a set theory concept might turn out to be enough to determine, strong enough to determine, look, there, if you allow any concept sort of that included all the first order theory, right? If you could somehow build the first order theory into a concept, I don't know that there's any natural way you can do this. But say, yeah, part of the concept is here's a concept of kind of structure. The following complete first order theory is true of a structure if it satisfies this concept. Of course, I guess that's, it seems to me possible there'd be a concept which was not really, wasn't instantiated. Its first order theory was fixed, and that there was some argument that it was a categorical concept. I mean, first order is very special. That's why I'm resisting going along with you. That I don't. First order, in what language, right? Maybe if you extended the language in some way, it would cease to be It determines all the first order truths in some language, but there's a stronger language that you might associate with the concept also, where it doesn't determine all the truths. So it depends what you mean by the first order theory. Depends on what your language is, and it isn't, as with the concept of natural number, it's not directly associated with the concept. I mean, nothing wrong if you include exponentiation, for example, with the natural number concept, which I think is perfectly fair for what I've been talking about, the concept. Then you're changing what's first order do. There's more than first order, and if everything is determined, so to speak, then it's fully determined. But first order just seems to me, in general, a special case.